Okay. Well, again, thanks for the invitation and thanks for the introduction. So I have been, as has been said, I have been working in this area for quite some time, and also, as has been said, so it's a very timely time to work on this, I think. But many of us are working in this area from slightly different perspectives, although overlapping, I think. So what I want to do is to really explain my very particular perspective on this and say some of the content. Most simply, I think I'm addressing a phenomenon. So the question is, what's the phenomenon one's addressing? At least if you think you're inspired by human cognition. And so I think the phenomenon I'm interested in here is that we can reason, but in particular, we can reason even on information which is uncertain and even on learned information. The important thing here is that the kind of knowledge I want this thing to succeed in is knowledge which can be learned. So the things which learning finds fairly easy. So that's the philosophical end. So the more technological question is simply the following, which I think everyone is aware of, that at the bottom there's a notion of what's the state of the art you can achieve with the single learning box, so maybe by deep learning. And the question is whether you can reason on this effectively and maybe reach conclusions which the single learning box cannot. I am interested in amplifying the power of standard supervised learning and seeing what reasoning can add. Okay, so that's so slightly more generally, so how does AI work? So I start from the phenomenon which I'm trying to capture, and so that could be supervised learning. Self-supervised means that the labels come from within the data, essentially the same thing. And then we have algorithms, data sets which are instructive, and of course we need computing capabilities. And so, I'm interested in specifying the phenomenon. Okay, so which one I'm trying to do a bit more formally than some. So I've been interested in packed learning, which is the formalization of efficient generalization. So you want to put on paper what learning does in terms of the fact that if you put more and more effort in, how much does the generalization improve? And just to explain why I'm interested in specifying the phenomenon, a bit more mathematically than some, I think what one gets from it is two sides. So on the one hand, you've characterized what you're doing. But I think it's also important that after you've characterized it, you know what you're not doing. So, for example, there are many things which people complain about as far as machine learning, like explainability, spurious correlations, adversarial examples, lifelong learning, which people are sad that standard machine learning boxes don't do, or that they're challenging to achieve. You have to work hard because humans, when doing supervised learning, can do some of this. But of course, the response is that, well, the formalization packed learning doesn't promise you any of these, so you shouldn't be disappointed. It's just, what the outcomes deliver is kind of what the theory promises. So in the similar spirit, I think there's a lot of value, especially when we're looking for what to do next in AI, to try to formalize what's the capability which we're trying to achieve. Okay, so I'm interested in reasoning on learned knowledge. And so the system I'm working on is one I've been pursuing for a very long time, called robust logic. And for this, I do have some algorithms, but some spectacular application which demonstrates it that's missing. Okay, so I'm very interested in pursuing that. So very roughly, if you're thinking of extending standard machine learning and trying to do more with it, then inevitably, kind of thing you'll do is to learn many boxes rather than just one. So we do want to exploit all the power of machine learning. We don't want to throw it away. We want to build on it and try to achieve more. So on the one side, we know we have some theory of what we want single learning box to achieve, some sort of power law of decreasing error. And so what one wants to promise with this robust logic is also some principles, some promises. And we want to combine learning and reasoning. And so actually, in one sentence, what's promised is that when you do some training on what you've learned, there's some guarantees on the error, that the training together things you've learned separately will be guaranteed to have controlled error in terms of the error of what you're combining. So that's very simple. Okay. Okay. So the question of whether learning is so powerful that we don't need reasoning, people ask that. So there are people who are reasoning deniers. Okay. So to answer that, we just have to I suppose demonstrate something. And so very quickly, so the problem I've been looking at, the AI problem I've been looking at as a real problem is word completion, that someone gives you a sentence, you delete a word, you have to find the missing sentence. So of course the point of this is that there's ground truth. There's a true missing word, there's a ground truth in this task. And also it's useful to take these sentences from like headlines from websites or newspapers, because they tend to be brief. So this is just some problems with some sentences I found happened to be on the Vietnam website a couple of years ago. Okay, so struggling shopkeepers at Ho Chi Minh City, traditional markets learn to sell. You have to fill in the missing word and then answer it online. And is this easy or hard for an end-to-end learning system which learns from the web? Answer is should be easy, because if you type in the key words in the sentence like struggling, shopkeepers, sell, and online, then you get 1 million results. Okay, so this should be easy. Second one, Barter surviving as classico leaves blank delicately poised. Well, this happens to be something about Spanish soccer. So you may or may not know what this means, but this is very easy because there are in fact 77 million web pages which deal with this. So this is something about the Spanish soccer league. So this is dead easy for anything which learns from the web. So let's try another one. So this says Saigon Football Club plan to send players to. Answer was Japan. This was the headline. And this happened to have very few search results. Probably when this first went up, this headline, there may have been 0. So this was a sort of a news event, something happened, and it was a rare event or never happened before. But presumably experts in soccer probably could make a reasonable prediction, but you would predict that an end-to-end learning system would not. So of course, one progress is that I'm trying to compare things with some standard end-to-end learning system, and now we do have one people discuss, which is ChatGPT. And at the weekend, I put these in, and ChatGPT kind of agreed with me. So every time I put the first one in, it got online. So online is dead easy. Every time I put in the second one, it got La Liga title race, which is perfect. And it was very confident every time we gave the same answer. And on the third one, it had no clue. Well, it did have a clue, so it always came out with train or train abroad. So if you send soccer players somewhere, maybe to train abroad. But if I put in various other football clubs from around the world, it never tried to venture a place to send them to. It always said to send them abroad. So, okay, so this is kind of just an illustration that intuitively we have some idea of that when you need to do some chaining of pieces of fact, several pieces of fact in a longer chain, then end-to-end learning finds that challenging. Okay, so so this kind of problem I've been interested in for a long time. So a long time ago, with a then student Loisos Michael, who some of you may know, so we did an experiment. So same thing, Wall Street Journal articles. We're trying to predict a missing word in the sentence. Okay, so we learned rules, but we wanted to learn rules which expressed real-world knowledge. So say knowledge about business, something like that. We learned these real-world rules, which weren't purely linguistic, and we wanted to chain the rules together. And the question was, can you make predictions about a missing word which are better than your baseline pure learning? Okay, so in modern terms, the question is, for these kind of problems, you can put them in chat GPT-3 and get an answer, but could you get a better answer, say on the factual questions, which chat GPT often gets wrong, if you do something else? And my conjecture is that you can. Okay, so this old experiment we did, which was kind of in the Stone Age. So basically, we chose 268 words, which occurred frequently enough in the Wall Street Journal database to be worth looking at. And then the ordering of the 268 words from left to right were that our system worked better and better as you went from left to right. And you should only look at the top two lines, E and D, the red and the blue line, and the difference on each word is how much better our prediction was than what our baseline learning system was. Okay, so on the left there were some words where in fact our system did worse, because for each word there were relatively few support of the learning was small. So anything you do other than your best effort at supervised learning will become noisy. There'll be sources of noise. So on the left, you're fighting source of noise, because this is clearly kind of the best thing to do is your state-of-the-art single black box learner. But if you reason, then maybe you can do something better. So I suspect that if you work hard enough, although how exactly you frame this experiment isn't so obvious, so should you give the same amount of time to the black box learner and whatever else you do, maybe you should, or maybe not. But that if you do some sort of reasoning on what you've learned, then there are chances for improving the accuracy of your predictions. Okay, so robust logic, I won't give it to you formally, but basically, so it's a natural extension of back learning, and one feature is that there are no probabilities computed, but you're distinguishing between statements which are probably true versus otherwise. And so this is useful in the large machine learning applications where the world is just too complicated to actually model accurately as a probabilistic model. Okay, so the learning algorithm you use, go to fourth bullet, is anything you like. So you use your learning algorithm as a black box. If you've got enough resources, you would use deep learning, but if you don't, then maybe you use something simpler. So the interfaces between these boxes does look like logic. You've got multiple objects with relations on them, so the interactions, okay, and then you chain the conclusions of these different boxes, which amounts to very simple kinds of reasoning. So the third thing is that partially specified worlds are very important here. The point is that your learning system may have learned with respect to hundreds of thousands or more features, but each particular scene you see has only got a few features in, and most features aren't specified, and you have to account for that somehow. Okay, and again, the last thing is the main promise is that there's some notion of soundly chaining the rules, which just means that if you chain together two rules, then the conclusion will be, the error of the conclusion will be guaranteed to be bounded in terms of the error bounds of the bits you've have chained together. So the system, one constraint, every part of it is kind of polynomial time. The black box learner, you assume, is efficient maybe in a heuristic sense, you don't care. But in everything else, you want to restrict things to polynomial time. So the kind of reasoning you do is very simple. It is a kind of chaining. But the question is, how much can you count for having some local quantifiers, partially defined features, and things like that. So just in pictures, so way to view this robust logic is that it discusses an example is a scene. A scene has got some, what I call just a token, two tokens, and some relations on the tokens. And so this asserts that a dog likes something, dog likes a bone. So in logic, you would have a rule like this, an implication. But in robust logic, the analog of a rule is an equivalence. So an equivalence is, do I have one? Yes. So it's a predictor for when something is a bone. So it's like having a neural net which predicts whether the missing thing is a bone. And the left-hand side is some possibly very complicated expression which tells you that if this expression is correct, you're very, very likely to see a bone. And if it's not correct, you're very likely not to see a bone. It's an if and only if condition. So the machine learning imposes equality rather than implication. But this is what machine learning is good at, equivalences. So there's no problem there. So we're learning equalities. Okay, so I'm not giving a full description here, just a few clues. And then we'll have a distribution, natural distribution over the scenes, which you see. So dogs liking bones may be very frequent in your world, or it may be rare. And you'll need to be correct on whenever things are highly predicted probabilistically. And so you'll have all these learned equivalence rules, and there's no enforcement of consistency among the rules. But when you apply the rules to instances, then maybe you'll find out that two rules are contradictory, and then maybe you learn your way out of it by updating one of the rules. So the logic activity going on here is only chaining rules to particular situations. Okay, so with the Wall Street Journal article, so that's just an example. You were trying to predict whether the right-hand side, whether the missing word in a sentence was price. And there was, I suppose this is neuro in the sense that this was the linear inequality with numerical parameters. You could put a deep network here, so this doesn't have to look logical. But the arguments are kind of logical. So for example, this says that the missing word is price. If there's another word which says that something else lowers this missing object and something else is a bargain. Okay, so if something's a bargain, usually the price is lower. Okay, so you've learned from lots of sentences in the Wall Street Journal some rule which kind of predicts what the missing word is price. And this isn't a pure linguistic thing. We're really trying to find relations among objects in the world. So the learning process is different from a language model. Okay, so just going back, okay, so this is what I'm doing. So one obvious question is whether the small experiment we did eons ago, whether if one did it on a really large scale, what one would get. So, for example, so the idea that on news items, something new, something very rare, one should be able to do better in using reasoning. Yes, that's clear. But but it may even be that you can do better using reasoning on very standard natural language tasks. So in some sense, this missing word problem I've been describing is a standard natural language task. So, so for example, a question is whether you know, if you regarded ChatGPT as your standard black box machine learning thing, you know, could you improve that by doing something slightly different, learning something slightly different, using GPT slightly different, and really get better predictions, exactly as the toy experiment did of some words in the Wall Street Journal. So this is so doing a natural language project along these lines is very tempting because you know, there's a lot of activity there already. But there's also a question whether there are other domains where one could demonstrate this. I know some of the people at the workshop are discussing some of this, so I'll be very interested in that. And so thank you.
Thank you very much, Leslie, for a wonderful talk. So we have a few questions. Maybe I'll sample a few of them, just being conscious. So Caleb Schultz-Kisby is asking, how is robust logic different from fuzzy logic or probabilistic logic? Both handle error in different ways and both support distributions of truth values, etc. Well,
I think, okay, so well, there are many probabilistic logics, and I think this one is different from, so it's not, yeah, so it's not a model where there are many worlds and you're trying to see with what fraction of the worlds this thing is true on. That. And the kind of theorems I have, I think, are just different from what fuzzy logic. Fuzzy logic, to me, thinks that is much more informal. Okay, so I believe it's different.
There's another.
It's a natural extension of pack learning. Maybe that's the way to put it.
There's an interesting question, I think, that links to your interest in evolution. So Nicole Singleton is asking, we've come a long way and took some brilliant minds to get there. Her concern is that it will make the human population lazy. We barely use our brains anymore, so the question is you know, if you can share some thoughts about where AI and automation and learning is taking us, maybe as a species, rather than not only from the AI perspective, but also.
You mean, does this leave any room for humans to do anything interesting?
Right, exactly.
Yeah, well, actually, personally, I'm not worried about that at all. So it may be that, having been in machine learning for a long time, I'm less impressed by these machine learning systems. Okay, I think, you know, what they do, I think, is you know, I find less surprising. You know, so they're done on a big scale. You know, they've got lots of data. And you know, and I think, as I said at the beginning, they don't do more. I think people give them more credit than they deserve. Okay, so just because you know, a machine gives you a sentence which isn't obviously wrong, you know, people are impressed. You know, when it's obviously wrong, people say the machine is stupid. But if it's a plausible sentence, people say, "Wow, you know, this is amazing." So I think people give too much credit to what AI is doing at the moment. So I'm not worried at all.
You're not concerned. Okay.
No, no.
So thank you very much, Leslie, for really